Okay, so hope all of you, did anybody not get an email from me last night? Here, you did not?
Oh, I did.
You did? Okay, yeah, good. So I know that there were one or two of you who registered late and were not in the first mailing list, so I just wanted to make sure. Yeah, so I took a little time to post the second assignment, but primarily so that we are in sync with what we are doing in the class. And just as I think the first problem we had already discussed a little bit. Take your. I've left it to you to look at the transport of a particle. In order to solve this, you may have to make a decision on what sort of quantized level you want to choose for the harmonic oscillator. Is for a high excited state, is it n is equal to 100, 30? What you got to choose that, and make a analogy or make the connection to the classical particle. Where how far in x does the particle start out, and then you have to make that analogy to compare the two. So if you choose n is equal to 30 or n is equal to 50, the wave function obviously will have a very large number of terms. If you know the wave function, the nth wave function of a harmonic oscillator has this Hermite polynomial, right? And times e to the power minus x squared by some constant square, and this has exactly n zeros, right? It has n nodes. But then, I mean, if you use any sort of plotting or MATLAB, Mathematica, I guess Python, they all have most likely this function built in. So you just call it and make it a plot, because you could set it up yourself, but it may be a little unwieldy for very large numbers of n. So just yeah. Okay, and the next two problems I've asked you to do is primarily to get some practice with the operator, the occupation number formalism that we have been talking about. And I just wanted to again repeat that in single particle, in all transport phenomena that involve single particle physics, this is unnecessary. We don't need to invoke this formalism. It is meant for the moment you go to two particles or more. So that's when the fermion and boson differences really appear. But then, because we are going to discuss a few many particle transport phenomena in this course, I thought this time, as opposed to the last time I taught it, where I introduced it at the very end, I thought it would be easier for me. It would be helpful, perhaps, to introduce it a little early, so that you can also use it in your projects that you might pick and such things, and get some practice with it. If you have not seen enough of this or have not used it in courses, I just want to assure you it's relatively straightforward once you get a grasp of what it is. It looks a little alien that you are dealing with, these objects which are not numbers or not functions, but just get some practice. This meant primarily to get some practice, but also highlight the physics of what is happening. So why are we discussing about this aspect? So for example, I just wanted to say that I've asked you to look at some if I look at say a state like this, you can see that there are two orbitals and each of them has one particle in it. This is the occupation number picture, right? And then these operators are acting on it. Let's say it is for bosons, so A2 will act only on the second orbital, right? That's the label. It's an annihilation operator. A2 dagger will only act on the second orbital, and so on, right? Right. So as you, so this is just to find. In the end, this will give you a number. Right. This will give you a number. This combination of operators here any combination of operators, AIs and AJs and so on, and between two states of a system in occupation number formalism is exactly identical to what you do when you write an operator, say momentum operator, whatever be it, and you take its expectation value, right? You take psi, psi star, and you integrate over x is the same meaning. So this is the expectation value of an operator p, momentum or whatever be it, is the same meaning here. So you're finding the expectation value of maybe a physical quantity that is modeled, that this combination of operators captures. So you know that, for example, the creation and annihilation operators in the first place were created by combination of your x and p coordinates, right? The momentum and the spatial coordinate for the bosons. So this will give you a number, and when you come here, I'm saying, well, do something like this, sum it over many j's, and then you may get things that are not necessarily numbers, but functions and such things. So, yeah. Okay. One of the things I wanted to kind of make sure we're clear is, all right. So, and for example, this problem may take a little effort and indexing and such things. So, yeah, and I can please ask me questions if you need clarifications and such things to solve these problems. Just as a very quick example of what such operator algebra could potentially do. So if I take a boson operator, which is say annihilation operator, and a creation operator of bosons, and this we discussed that this is let's write it B1. All right. Let me just summarize again, just for purpose of reminding ourselves of, and also maybe help with assignment here. That here's a summary of all the rules that these operators have to follow for bosons. It's just three relations, just three of them, and so if I take the annihilation operator of the ith orbital, and I take the annihilation operator of any other orbital j could be equal to I, what will I get here? If both are annihilation operators, you will get a 0. So and this is for bosons. What does it mean? If I take bi, bj minus bj bi, they are equal. These two are equal, right? And in specific example, if I take, say, B2, B6, and I have, B2, B6 minus B6, B2 is equal to 0. That means let's operate it on a state. So let's say I have, 0, 2, 6. Okay, let me write some numbers down. Okay, and maybe you can help me with it. 3, 1, 2, 5, and so on. Here's an occupation number state. Orbital 1, orbital 2, orbital 3, and so on. Right? Let's take this and operate it here. B6, B2, right? So first, operators must be ordered, so they are in this order, right? First, B2 must act on the physical quantity going on is this operator is acting on the state. What will it do, right? B2 will act on which orbital? 2 orbital 2, right? So it will just act on this, right? And it will go search and look at here how many particles are sitting here, right? And then it will annihilate it by 1, or otherwise reduce it by 1, right? So 2 will become 1, so it will convert it into 1, 5, and everything else remains the same. But then it will also give you a coefficient, because here's the relation. When annihilation operator acts on a state n, it gives you square root of n times n minus 1, right? Right. So it reduces the state, but it gives you this normalization coefficient. So it will give you what? Square root of 2, right? square root of 2. And then now on this will act B6. And B6, this is a number, so that will just go away. Operators only act on occupation number states. They don't care about numbers or even functions. If you have a e to the power ikx sitting here, it doesn't care. It doesn't act on functions. It doesn't act on numbers. It only acts on occupation number states. In other words, the word people use is these operators live and do all their business in this space of occupation number states. They don't live in the state of real space or momentum space or function space or number space. They live in the occupation number state, right? So just to be clear, so this will come in handy when you actually solve the problems here in this assignment, just to be clear. Okay, so then B6, what should it do? It will go and let's see, 3, 4, 5, and 6, right? So it will do. It will reduce the number here by 1 again, right? So you get another square root of 2. So in the end, you get what? 2, 3, 1, 1, 5, and so on. Right? This is the final state. Now, what this operator relation says, commutation relation says that if I had first operated with 6 and with 2, I would get the same final state. That's the physical meaning of it, right? Right? Is that clear? So that's the operator algebra, and this is true only for bosons. Right? If you go to fermions, actually, let's finish the discussion of bosons. So that's one relation. Okay? The second relation is if I do the same thing but with annihilation operators, I still get a 0. If both are annihilation operators, it's still 0. It doesn't matter which order you create or destroy these particles in an orbital. The end result is the same. That's the property of bosons. So, yeah. Okay. And the third relation here is Bi. The only time when the commutator is non-zero is when you create and annihilate. So that's when, if you take annihilation first and creation later, they don't commute, and the remnant or the remainder is 1. So, and this is the quantum condition. If you make the right hand side 0, you get classical physics again, classical thermodynamics of bosons and all that. This one maintains quantum, this is the quantum mechanics, and this is equivalent really to x comma px is equal to IH bar of the harmonic oscillator situation. It's actually, that's where it came from, because if you go and look at what is my annihilation operator, what is my creation operator, how are they defined in terms of these two, this is where it comes from. Right? Okay, so that means I can kind of treat these two minus b dagger bi is equal to 1, and then after that I can, these are, though they are operators, I can move them around. I can do 1 plus b j dagger bi, but all that I need to do is make sure that I don't flip the order of the two. That's all. Right? I must not flip the order of the two. But other than that, I can move them around in equation and do all that. I can take power, 5th power, 8th power, whatever I want. But if I take a power, again, you must make sure that square is, you don't have a choice. The ordering has to remain the same. So that means this is one object, bi, bj dagger, then again the same thing, bi, bj dagger. Right? Does it make sense? Okay. And this may not be equal to, again, bj, if I flip it, it's not the same, right? So, because this combination of one annihilation and one creation doesn't commute, right? Sorry, just to be clear, is this correct? I think somebody should have corrected me earlier. This is correct only if I is equal to j, right? So ideally this is delta ij, right? Right? If they are different orbitals, there's no business. They will always commute, right? But so I should really write it as delta ij, right? And this is delta ij. Yeah. And so if, on the other hand, the same orbitals, then okay. And physically, this quantity is really giving you bi. Let's say that is acting on, I make it 3, and I have 2, 1, 5, 6. So what should that give you? B3 dagger B3. So remember, this combination of creation, or rather B dagger B is the number operator. It just, is the number operator. You can actually apply it and see what you get. You will get the number. So see, this is third orbital, so it's going to act on this. And the claim is it's going to give you 5 times the state, right? 6 and so on. The eigenvalue of this operator is number 5, right? And you can see it will give you that because you first apply B3, you get square root of 5, right? And that becomes 4, right? And then you apply B3 dagger, it increases, and you get another square root of 5, so you get 5, right? So this is just the number operator, right? And you will need some of these in the problem to practice a little bit. Right? So these three are really the constitutive relations that you need, and then most of the algebra follows from here. And for fermions, on the other hand, we are using this anti-commutator relation, meaning this curly bracket, and we are using C's, Cj dagger. Okay, right. So again, for fermions, if I take Ci and Cj, I get a 0. But now it's an anti-commutator. What does that mean? It means that if I take Ci and Cj, instead of minus, you get a plus in here. The anti-commutator has a plus in between, and Cj, Ci. That is equal to 0. Right? Not minus. So bosons is minus, fermions is plus, and this is what really ensures or captures the physical difference between fermions and bosons, the sign change, right? And so that clearly you can see now what this physically means. Maybe you can tell me what does it physically mean if I take the is equal to minus Cj Ci. Physically, what does it mean? What does it do to a state if it acts on a state? Right? If you annihilate one state followed by another, right? And if this is the order, if you first annihilate state 1, orbital 1, and then 5, compared to if you do 5 and 1, if you have this, the order in which you do matters, one of them will give you a negative sign, right? Does that make sense? I mean, they are not exactly the same. It will flip the sign of the final wave function or the final state. So that's, and that is why from here, if I and j become equal, if the orbitals are the same, Ci, so you get 2 times Ci squared is equal to 0, or in other words, Ci squared is equal to 0, and that is your Pauli exclusion principle that you cannot, well, that and Ci dagger square is equal to 0 as well. From this, because Ci comma Cj dagger, that is also 0, right? So these are the two relations, and Ci dagger square 0 means that that's the Pauli exclusion principle, that you cannot put two particles in the same state. So that's right. So and as a result, anything higher than that would also go to 0. But anyway, okay. So and finally, the anti-commutator of Ci comma Cj dagger is equal to again 1, but now it's Ci Cj dagger plus Cj dagger Ci is equal to 1. So it's different. The plus sign is very important for the fermions. So excuse me. Yeah, question. Is that also Kronecker delta, or just oh, thank you. Sorry. Yeah, I keep skipping this. Yeah, so it's a Kronecker delta. That's right. Ij. Correct. Yeah, thank you. So one rather useful thing is if I have just a collection of boson annihilation operators or creation operators, but it's all annihilation or all creation. So say B2, B5, B8, whatever, right? You can reorder them in any way you want, and the sign will not change. But for fermions, you have to be careful. For every flip, you must have a -1 sign. Okay? So if I have C2 dagger, C5 5 dagger and C8 dagger. And let's say for whatever reason I want to flip these two, okay, for whatever reason, then the sign of this will remain the same, but if I flip these two here, I'll get a -1 in front, you know. So that's, yeah, right. Yeah. Okay, so some, you know, few things about these operators, and then towards the very end of the last class, we discussed an application of this, and this is I've also put it down here that you can try your hand at it. The most basic, you know, electronic band structure calculation, you can write it formally in terms of the creation and annihilation operators. This is the tight binding model of any solid, you know, electrons in a solid. And traditionally, you know, in a single particle quantum mechanics, without this operator algebra that we are discussing at this point, the way to think about transport, or rather, you know, electronic energies allowed in this system was you can say that there's the on-site energy of E0, and the hopping energies is, say, minus T0 and minus T0, and these are in solids, we are talking in terms of few electron volts typically, right? This would be few electron volts. This may be much smaller, you know, hopping energy, and so in standard single particle, you know, solid state physics courses or quantum mechanics courses, the way you solve this problem is, say that I know that I'll have a state which will be a block state, so it may look like e to the power I k x n, where k is a wave vector, you know, over square root of big N, where big N may be the total number of atoms, a number of sites here, times you know, basically if the particle was sitting only here, we label it as n, you know, and this is n plus 1, n plus 2, n minus 1, n minus 2, and so on. So this is what you say that let's try this wave function for my Hamiltonian, and the Hamiltonian is actually pretty straightforward. It's if you are sitting in state n, you know, well, okay, I think I want to. So you see the on-site energy is E0 and hopping energy is minus T0, right? And so your Hamiltonian is really H psi is equal to E psi, right? And when you try to solve for the eigenvalues to get the band structure, what you want to do is say that if this is a wave vector which is going to become effectively a 2 pi by wavelength of the electron, what are the energies allowed for the electron now in this sort of a periodic situation with on-site energy E0 and minus T0, right? So here we can, in the single particle picture, I can take this and basically plop it in there, right? And then this is, by the way, your block theorem, right? So this is actually a periodic function because n is exactly equal to n plus 1. The states are the same, you know, they're sitting at different points. And this is your modulating function, e to the power I kx sort of thing, right? And when you plop it in here, what you really end up getting is this relation that E0 times Cn minus, these are the, okay, let's call this as C sub n. Not an operator, sorry. Just want to make sure. This is just a coefficient. Cn times n. So in other words, I write my wave function as a sum of n, C constant times n, right? So you get this minus T0 Cn, say minus 1 minus T0 Cn plus 1, right? And so have you seen this or not? I just want to make sure. Basically, what you're doing is you take this and then you take an inner product with state M and all that, and you get those equations pop out basically. And physically, at least, it should be appeal to what. So this will be your, you know, energy, allowed energy. So essentially, this is your left side. That's your right side here. You know, allowed energy is on the right side. So. And these are unknown coefficients. You have to solve this. Now, again, you will get the same thing for Cn plus 1 and so on, right? And the way we solve it in traditional single particle quantum mechanics is we have this set of equations. You write it for n plus 1, n plus 2, n minus 1, and all that. So you get this whole series of linear coupled equations, right? And the way you solve it is you put it into a matrix form, right? And the matrix will look, the diagonal elements of the matrix will be E0, E0, and E0, right? And just the next term would be a minus T0, a minus T0, and a minus T0, and then you get a 0, 0, and so this is nearest neighbor hopping, okay? And zeros and all that, right? Yeah, so times a combination of coefficients. Let's say this was your, nth n, this is n minus 1, this is n plus 1, and so on. You can think of it as an orbital state. This also as an orbital state. Minus 1, and so on. So this is just the overlap value. If you go from n to n, the electron is sitting on the sides. Its energy is just E0, right? But if you go from n to n minus 1, your energy lowering is minus T0. That's the physical meaning of your Hamiltonian in the matrix form, right? Okay. And you write this out as Cn, Cn minus 1, Cn plus 1, and all that. And you have to solve this eigenvalue problem now, Cn, Cn plus 1, and so on. Right? So you solve, when you solve, you find the eigenvalues of this, and you find all the allowed energies for the system, right? Now, it's absolutely unnecessary in this particular simple linear chain picture to write this whole matrix out, because you can actually solve it right here by taking a guess, and that guess, you don't have to guess. If you know Bloch theorem, you're through. Bloch theorem gives you the answer right away. Bloch theorem says that your coefficients are of the form, let's call it some some constant times e to the power I k x n. That's what it's saying. It's of this form where your x is the length and this n minus 1 is the index of it, right? Does that make sense? I mean, it just tells you that Cn's are of this form. And so let's say I have Cn here. Oh, sorry, I think I should have written this here. So this will be a Cn here, the coefficient. Sorry, yeah. Okay, so that's your central equation for the hopping in single particle picture. And so if I substitute in this equation, plus 1 is equal to E times Cn, and I substitute Cn is e to the power I k x n, then this one, Cn plus 1 will be e to the power I k x n plus a, where a is the lattice constant, right? The distance from n to n plus 1. Do you see that? I mean, so the Bloch theorem is telling you that you should just use it and you'll get the answer in a step, and you do. So here you get e to the power I k x n minus a, right? And this is also e to the power I k x n, and you can see that all these will cancel, and the only ones that will be left is e to the power I k a and e to the power minus I k a, right? So they'll all cancel out, and as a result, your energies will be E naught minus T naught e to the power minus I k a minus T naught e to the power plus I k a is equal to your energy, and the coefficients are gone. And this is your energy dispersion, or the band structure of the electron in this solid, E versus K. Yeah, obviously it looks like you have complex numbers, but you can see this will become a cosine function because it's in that form, and so it becomes E naught minus 2 T naught cosine of Ka is equal to well, that's the energy band structure. Those are the allowed energies for the electron in this periodic solid in the tight binding model. Obviously, you have made approximations in the model here, right? If, on the other hand, you have a finite, let's say a polyacetylene molecule which is 30 nanometers long, it's not an infinite chain. Okay, you can write, if there are 50 sites, you can write your 50 by 50 matrix and solve it. You can do that. If it's a chain of 5, you can also solve it, right? Does that make sense? I mean, but any quantum mechanical problem, you can solve it this way. Right? Solve it as in you find the eigenenergies, and once you put it in this matrix form, you can go to some sort of a matrix calculator, Mathematica or Python, whatever, and it will give you, for each eigenvalue, it will also give you the eigenfunctions. What is eigenfunction is just the collection of these coefficients, and you're done. The problem is completely solved then, meaning every physical quantity you want to know about the system, you can get from this set of eigenvalues and eigenfunctions now. Right? So let's just before we go to the many particle picture of it, let's just look at what does it physically mean. Physically, if I have this same idea carries over to band structure calculation of any sort of periodic crystal, graphene, silicon, gallium nitride, whatever you want, you can calculate the band structure in this way. This is the simplest model, and each orbital. So here our assumption is at this side there is one orbital, here this side there is another orbital, and so on. Right? If I have a chain of one type of orbital, let's say it's the s orbital here, it's the s orbital of the atom, and so on, then each of these orbitals per site will give you one band, right? One band, and here's the band of this orbital. Right? If I had two orbitals here, maybe an s orbital and a p orbital, right, in each site, then for the p orbital I'll do the same business again. I get another band. Right? So if I have one s and three p orbitals, which is typically true for most semiconductors like silicon or gallium arsenide and others, is sp3, one s and three p orbitals. Then you have four on-site energies, E1, E2, E3, E4, right? Four on-site energies, and you can have multiple hopping energies. An electron may be able to hop from S here to P there, and so on, right? So you have all these. But if you have a periodic crystal, the size of the matrix that you actually need to solve is actually given pretty much by the number of orbitals per site. So for example, if I have four orbitals and each of them has two electrons, like what you have in actually silicon, then your matrix is 8 by 8, and you solve it and you get your whole band structure of silicon, the entire EK diagram, right? Those who had taken 4070 and the last semester, you have done that, I think, if you remember. But you haven't, you can go back. I've linked the course assignments, all that, so you can have a look at it. And so, okay, so we will do in the next assignment after this one, you will do this for, say, graphene or 2D materials. That's actually a very easy calculation, much easier than silicon. So, and you can calculate the entire band structure, and then after calculating the band structure, you can investigate transport and other things in it. Okay, so just to clarify, if I had two orbitals per site, just as I said, S and P, and let's say I have a situation for whatever reason that the electrons can only hop from S to S and from P to P, and they cannot hop from S to P, for whatever reason. Right? This is a made-up situation. It may be able to hop there. It will just add another term to the business here. But if so, you can see that my band structure will look slightly different, right? I mean, I'll have to write TS here, is the S orbital on-site energy, and here it will be TSS. It's hopping from one S orbital to another. So it's the hopping energy lowering because of hopping from S to S orbital. Similarly, I will also have a EP minus 2T from P to P orbital cosine Ka is equal to E band. Let's call it a P band, right? This is the S band, right? Does that make sense? Exactly the same business, right? So just stuff is happening in parallel, and I try to. So one of the things that happens with P orbitals is, again, I just want to. This is just an example, and most of the times this is what happens. P orbitals have nodes, plus, minus. Right? Then the next one is typically minus, plus, and plus, minus, and so on. So what happens then is the let me say the end result of that is this one actually ends up flipping a sign. That's what happens. It flips the sign because of plus. Basically, when you take the overlap integral here, you get a minus sign, so that gives you a plus here instead of minus here. It's not terribly important, but I just want to kind of say this can happen in many situations. I'm trying to build up towards again a semiconductor sort of picture, right? And now if I were to plot these two bands, the physical meaning of this hopping and all this stuff here is the following. So I have k, which is your wave vector of the electron. The electron that is moving here has a certain wavelength, and 2 pi by the wavelength. That wavelength is this k, right? And essentially, this function is periodic between pi over a and minus pi over a. These are then we call these as a Brillouin zone edges, a Brillouin zone edge. This region from minus pi by a to plus pi by a is called the Brillouin zone, or the first Brillouin zone. And if I were to plot these, so cosine, let's see, cosine is at 0 is 1, right? So you get E0 minus this. Okay, so it reaches a minimum, right? This function reaches a minimum, and that function reaches a maximum. So, it will maybe. I actually let me do it this way, okay? So, okay, I'm going to again say that let's say my s orbital energy is here. It may be a 3s orbital, and this may be a 2p orbital. For example, I'm just making stuff up at this point. This is EP, this is ES. This can change depending upon which atoms you choose and which material you're looking at and all that sort of thing. Let's say here's the situation. S orbital ES, which is the center energy of that band, is here. And EP, which is the center energy of that band, is here. What do I mean by center energy? I mean that if the atoms were very far apart, they were not in the solid, this would be energy of the electron. Right? There would be no hopping. This term is gone, and that's the energy of the electron. And so ES would be here, EP would be here. But now that you have formed the solid, I want to plot this, and if I plot this one, you can see it basically spreads around the center energy, right? It goes as a cosine around it with a bandwidth of 2 times TSS. Right? That's the hopping energy. That's the bandwidth. Similarly, for p orbitals, for this band, you get. Oh, sorry, was it 2 times or 4 times? 4 times that, right? From minus 2t to plus. Cosine goes between minus 1 and plus 1, right? Similarly, for the p orbital, it'll do something like this. Okay? This is just a cosine function. And in this solid now, so these are all the allowed states of the solid. And let's say you have exactly 2 electrons per site in this solid. You can, because you have 2 orbitals, you can have 4 electrons in principle. Each orbital can hold 2 electrons, up and down spin, right? Each orbital is 1 quantum state. It can hold two electrons. Let's say I have only 2. Then again, if I had a finite number of sites, which is big N, you know that now that there are exactly n number of these energies here. So the number of sites here is exactly n. Here's one orbital. This is a p orbital. Separation between them is 2 pi over the length of the crystal, right? The total physical length of the crystal. Okay. And all right, so this is almost a repetition of last time, but I wanted to kind of build it up with a multi-band picture, a multi-orbital picture. So if I had 2 electrons per side, then you can see that I have 2n electrons, and I fill up this band completely, up, downs, and all that, right? And I have this one empty now, all right? So there's a gap between the two, right? And this is a band which is allowed, but it's empty. This is a band which is obviously allowed, but it's full. So we call this as our valence band, and this is our conduction band. This is a very standard model of all semiconductors. standard model for most semiconductors. And you can see that the orbitals have to line up in this way. If not, you don't get a semiconductor. For example, you may get a metal or a semi-metal, or if they could overlap, they could do all kinds of things. Yeah.
So the minus T, so TO reflects the strength of, so it's the amount of energy required to hop, right?
Yeah, it's actually the amount of energy that the electron, there's the amount of lowering of energy because of the hopping. Because when the electron is able to spread out, it will lower its energy. The system lowers its energy.
So larger TO makes it easier to hop.
Or another way to say that is, if it is very easy to hop, then your T is large. So that's probably a better way to say it. Basically, if your electrons are not very confined, if they can very highly mobile, then T0 is large.
And the bandwidth is proportional to this TO.
Absolutely, yeah.
So
That's a very important point. Bandwidth is proportional to the ease of hopping.
Easier to hop means a longer bandwidth, so more steeper.
Exactly. So all these are connected. That's right. So if I stretch, if this is large, then this stretches out, and your curvature here goes down. So the effective mass is small. Its electron is effectively lighter, and so it can move faster and has higher mobility and all that sort of thing. Absolutely, this is all connected. And okay. Now, if your s and p orbitals are such that they are much closer to each other and T0s are large, then you can see the bands will overlap, and there will be no gap. And that would be either a metal, typically a metal, or sometimes even it can become a semi-metal if the overlap is in different places in K space. Yeah.
So in this model, what parameter controls the gap? Like what is the proportion?
Oh yeah, you can see from here, right? You can calculate exactly what is the gap. It is ES minus 2T, right? Minus EP minus 2. Sorry, this is minus 2. Sorry, EP plus 2T. Right? So you can see this is actually your gap of the material, right? So you can calculate it exactly, right? So yeah. So tight binding, you can get all these answers exactly, and this is nice, but remember it's a model and it has some limitations. But it illustrates most of the physics very nicely. And you can tweak these parameters. Essentially, you can do this either from first. Typically, what people do is you can do DFT, this density functional theory, and you calculate it from first principles first, the band structure. Then you find what are these parameters to fit it. Why? Because DFT is very computationally intensive. Let's say I want to track what happens to this material when I apply a voltage or a field. Then I can't be running DFT every time I change the voltage. Whereas if I'm in tight binding, it's very easy because you have the full model to go, right? And it's a compact, simple model, and you can use it to model transistors, lasers, LEDs, all that. So typically, it's heavily used. But these parameters that go into this tight binding model could have come from either DFT, or many times what people do more these days is experiments. You measure it. You can experimentally measure the entire band structure. If you go to Duffield Hall, in Professor Kyle Shen's group, they do RPES. They measure this entire band structure EK diagram directly, experimentally, and then you find out what are the ESs and ETPs, and you're done, right? So yeah, that's a question.
I mean, this depends on the symmetry. Like it has to have your structure has to be pretty symmetric to use the tight binding model. Otherwise, you use
periodic. The only thing you need is periodic. Every other thing it's able to handle, meaning I think maybe I'll just illustrate one. And if I have a situation where I have, again, periodic, this is the lattice, which is, devoid of any matter and all that. This is a set of points. And to set this set of points, let's say I have a silicon atom here, an oxygen atom there, and maybe a nitrogen and some other germanium, right? And they are in some form here, right? Some complicated structure. But as long as this is repeating, tight binding is good. You can use it. But if this structure here, this combination is different from here, then you can't apply it.
Okay, but you still have to compute the eigenstates for each of those.
Absolutely. So for each block, each unit cell, you have to calculate that Hamiltonian. We did it in a very simple way here, but generally you would have, if you have 8 electrons, for example, in silicon. Silicon is a relatively complicated crystal. I mean, well, it's simple because we understand it so well, but if you look at it, it's way more complicated than a single linear chain. And you have 4 atoms, right? And 2 atoms per basis, really. And yeah, as long as it's periodic. If it is changing from site to site, then it's an amorphous solid. It's not periodic, or if it is polycrystalline, this part is crystalline in one way, that part is crystalline in another way. That's polycrystalline. That's different from amorphous. These are all different classes of solids, right? Amorphous solids, Bloch theorem doesn't even apply. You can't even start here. They have a whole different way of dealing with transport. Mott had a way of I hope we'll have some time to discuss that a little bit later. But polycrystalline, we can actually apply in blocks the this theory, and then say quite a bit of things by saying that there's scattering at the interfaces. But if the whole thing is periodic, no matter how complicated is each unit cell, it's no problem. You can apply this and get the whole. You can apply tight binding for all of it.
And are you going to generalize this for 3 dimensions as well?
Oh, and absolutely. So what I'm suggesting is, in the previous course, I have an assignment problem. I'm going to send out an email then. You can look at it, and there's solutions. I can provide the solution. You can see how it's done for, say, silicon, for example, or gallium arsenide, for example, and you can see how you have to solve that 8x8 matrix. I want to, yeah, I think let me do that, because if I spend that in class, I will have less time to talk about transport. But as long as you get this idea, we can talk a lot about transport now. The details of it, obviously, if you want to understand the 3D material, you have to look at the 3D matrix. Let me just say that it's no difference from what we did here. It's just a bigger matrix. Conceptually, there is nothing novel after that. Yeah.
Is that a sci-fi symmetry? Is there a truly example in a solid where you have only PP hopping?
Only PP hopping. You have to think a little bit, yeah.
Thinking about symmetry, you should always be allowed at least one SP hopping combination.
It really, let me think a little bit, because I'm in semiconductors, we mostly are dealing with S and P and inter-S and P hoppings. If you're talking about some superconductors, a lot of them involve d orbitals and d hopping and px py hopping. So there are px plus I py hoppings and all kinds of. So yes, I'm pretty sure there are some where you have pp hopping only and s are not involved. Something like that. What am I thinking? Here's a great example: graphene. Graphene is all p orbitals. The pz orbitals, and it hops from one side to another through completely pz orbitals. S orbitals just hold the crystal together. They are not involved in transport at all. That's a good point. in the next assignment you will solve it and see. In fact, I had I think asked this in probably the last semester course too. The graphene band structure. It's all p orbitals. So, yeah. Yeah.
Was the Hamiltonian E6n/6n times larger than the 1D case?
The Hamiltonian.
In 3 dimensions.
Yeah. So maybe since we are talking about it now, I'll just write down the conceptually how would one do that and how the Hamiltonian looks. Here's a silicon crystal. All right, silicon. It's a 3D crystal. It has tetragonal bonding. And the bonding occurs because of an s orbital here, a px and py and pz, and they hybridize and form this tetrahedral bonds. And the Hamiltonian for any tight binding model, this is the way you typically would go about doing it. In silicon, there are 2 atoms per basis. There are 2 silicon atoms per basis side. And this is one lattice point. Then you go here, here's another lattice point, here's another lattice point. But the basis has 2 atoms, 2 silicon atoms. So, so you can write s orbital in site 1, atom 1 and atom 2. There are 2 atoms. S orbital of site 1, p orbital of site 1, p orbital of site, px orbital, py orbital of site 1, and pz orbital of site 1. I'm just writing out all the possible orbitals right now, right? Similarly, I write s orbital of site 2, px orbital of site 2, py orbital of site 2, and pz orbital of site 2. It's a very big matrix now, so it's out of the. Okay. So these are all your possible orbitals now, right? In which is repeating. This thing is repeating again here, 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 here. It's repeating, right? And you know these three repeating lattice vectors. Here's one vector. Okay. Here's another. You know these vectors. I mean, there could be more. Nearest neighbors. How many of them? A2, A3, and all that. You can have more, right? And then on this side, I write the same thing, but in because I want to hop from one orbital to another, I write it this way. Does that make sense? Yeah? You can write it in any order, but it makes a little cleaner, picture if I write it in one. Px1, Py1, Z1, and so on, right? So you see, it's an 8x8 situation now, right? This takes into account, just to be clear, all the hoppings, within this cell, right? Does that make sense? Within this cell, this is what it's doing. So let's see, S1 to S1, what will that do? It will just give you E of the s orbital, energy of the s orbital of silicon that is involved in this bonding. Similarly, you go down here, S2, right? E S2, S2. So that will give you energy of the s orbital, but they're the same atom, so it's the same now. E s orbital, yes, they're the same, right? Similarly, Px, Px1 will give you p orbital energy, right? Py, Py1, p orbital, x, y, z don't really, the on-site energies are not different if you have just x till they form the chemical bond. There's no difference, right? And now all these other terms, so your diagonal elements are already known, and then all these other terms are due to hopping from one to another, right? Does that make sense? Everything is now about hopping, right? So you go, if you are going from px, if the electron is sitting in px orbital of atom 1, it's px, maybe the px orbital of atom 1, and it's going to hop from here to s orbital of atom 1. So it's within the same site, from s orbital, the same site to it may be 0 because it's orthogonal state, right? It's not allowed. On site, at the same site, maybe it's orthogonal, maybe it has some numbers. So all these numbers now, but px1 to 1 could be 0, but if you go px from 1 to s of 2, right? Yeah. From here to there, right? That's the linear chain hopping, like here to there, right? So you can write it maybe as px1. So I can write it as v hopping from, p orbital to a s orbital, some energy, or t. I think we have been using t, so maybe t, right? And there's some lowering of energy, and it will actually have this formula e to the power I k, which is a vector dot this vector. Does that make sense? If you're going from here to there, this is the generalization to 3 dimensions. All of these k's and these x's become vectors now, right? Does it make sense? So k is the variable. You are going to solve this as a function of k, the eigenvalues as a function of k. But these are fixed, because in a crystal, the distance here and the direction is all fixed. So it's fixed. And okay, so you basically have to write this whole thing out, and then it looks in the linear form. It looked like that, but now it looks in the matrix form. It looks like this for the 3D, and you ask then what are the eigenvalues of this as a function of k, this whole matrix, and you will get it as a function of a vector k. In other words, you will get it as a function of kx, ky, and kz, all three. All three directions. The electron can move in any direction, but if it moves in one direction, it will have a certain energy dispersion, maybe like that. If it moves in some other direction, it may have some other dispersion. So it can, depending on which direction it goes, it has different band structure. So I will suggest you look it up and read it up, but yeah.
Okay. So, wait, what k is there for the negative t, the I, kx?
You mean this k?
Yeah.
Yeah. So what I meant to say is here's, this again comes from the Bloch theorem that because I'm looking at a hopping from, say, let's just say px, py inside 2 to s orbital inside 1, So then there's a physical distance between the two, side 2 to side 1, there's a physical distance, and that distance, let's call it a vector A, right? And the hopping term here will become minus t hopping between s and p times e to the power, either minus or plus depending upon if I go this way, I could go the other, So it will become either plus or minus I k dot A. Here it was just ka because there's only one direction, but now here it's a vector. So A is a vector which is going perhaps like this, but k could be anything, meaning the electron could be going this way, could be going this way, could be going this way. So it's a vector, and depending upon which direction it's going, you will get different eigenvalues. So
and when you diagonalize it, you'll just get the energies for each of those states.
Yeah, as a basically you have to if you are extremely lucky, you may get an analytical expression as a function of k. But if you define the kx, ky, kz, you can say that I want to go only along the 1, 0, 0 direction of a crystal where kx is changing, but y and z are not changing. Then you will get the energy EK diagram along the 1, 0, 0 direction or the 1, 1, 1 direction. So in silicon, for example, the conduction band minima are along the 1, 0, 0 direction. In germanium, it's along the 1, 1, 1 direction. I mean, all these. Yeah, so, okay, so, yeah.
This k is the crystal momentum.
Exactly right.
Associated with that, right?
This is the crystal momentum, and it is because you see in a solid, your electron momentum is regularly interrupted by the presence of atoms. So the net momentum of the, net physical momentum of the electron is composed of, if it was a free particle plus all these, scattering it is receiving from all the.
Like an average.
Yeah, it's actually not average. It is precise, but it is composed of also all the. If your lattice constant of a crystal is A, then you have, this is what's called the reciprocal lattice vector, right? And the electron, every time it interferes, every time it reaches A or, wavelength of A or 2A or 3A, right? A or A by 2. So wavelength is this or this or this. It interferes very strongly, right, with the crystal, right? And therefore, every time you have so essentially this k that we get in the band structure is composed of a free k. It's composed of a little bit of k plus g, k minus g, k plus minus 2g, and so on. It's a combination, and there you can actually calculate for any point here how much of a free electron k is it, how much of the first scattering, how much of second scattering. These multiple ones go down very fast. If you are at a point, for example, if you are at this point, which is very far from other band edges, this will be primarily like a free electron. It's not almost aware of the crystal. Here, for example, in this picture, it will be heavily affected by the lattice. So these are mixed states. It's not a free electron state anymore, right? So yeah, okay, yeah. Okay, so I want to kind of say that the reason I brought it up is because I have asked you a problem to solve a problem in the assignment more for practice of this operator algebra than for this understanding of band structure, but that's something I would suggest you, if you have not had exposure to band structure, or even if you, I'll send out this link to write up. There's in fact, a full chapter in the handout here that I had posted, which talks exclusively about the band structure. Sorry. Right, where are the notes posted again? So. Okay. So, if you read, for example, this chapter 8, you will get quite a bit of the information about what I mentioned here, about bands, band gaps, masses, all that stuff from a tight binding picture and also Bloch theorem. And there are many other ways of doing band structure, tight binding or K dot P, all that other things. So those details are not going to be very necessary in this course, but at least how the band structure develops is important.
If we wanted to model an indirect band gap semiconductor with the tight binding, where would we add the phase to shift?
You will not have to. Okay. The indirect will come out from here. It will come out from the combinations of your sp orbitals and the weights and everything. It will come out from there. If your model is right, it will come out. Yeah. You don't have to do anything separate or special for that. Okay, so what I've asked you to do though here in this problem is to kind of write the Hamiltonian in an operator formalism. Okay. Now let me ask you a question. Here's a situation where I have all these states occupied. I'm looking at a semiconductor maybe at very low temperature, such that the carriers don't have a chance to hop and all that, or to thermally excite themselves to the next band. And this band is completely filled, and that is completely empty. Maybe you can. I want to ask you, how do I write in this occupation number picture, the state of this whole system? How do I write it? In the occupation number picture, right? How? I mean, there are many ways to do it. You maybe can help me write it. So yeah. So these are all electrons, right? And well, some of them are occupied, some of them are empty, right? So so I can create this whole big sort of picture, right? And say that.
For each energy.
Exactly. For each orbital, what do I mean by orbital? Every point here, which is separated by 2 pi by L, is this is an allowed orbital, right? And I can write, maybe I say, well, I'll make space for here. These are all for my, P band, and these are all for the S band here, right? Right? And in that, I have all these sites going from minus pi by A to plus pi by A, right? These are all the sites, and actually each site can hold two, plus spin and minus spin, right? Does that make sense? Right? Okay. So I can write here, for example, let me write this way: 1 with a p orbital with a up spin, 1 with a p orbital and a down spin, for example, right? And so on, right? And actually, if you see this, all of them are ones, right? And but then, I should label it which one of the p orbital it is, right? Maybe I write it as minus pi by A. So you can see that there are all these indices. You don't have to write it, but I think we can realize that there are this many orbitals, and each of them has some index. This one has a momentum index of maybe minus pi over A and a spin index of up. Then next one is minus pi by A, spin index of down, and you have all these things then, right? And all these are occupied. So how many of these there are? There are exactly 2n, right? Exactly 2n of these, and each of them is 1 at low temperature, 0 Kelvin. And similarly, all of them here are zeros, right? Right. So that's the occupation number picture of a semiconductor. And it's in the occupation number picture, you only have information about the indices and all that. And it's understood that you have already solved your problem. You already know what are the energies of each of these. You know that band structure already. That's known. I mean, you don't have to. Does that make sense? I mean, it's not giving you the information of what is the energy of that state and all that at this point, right? You're saying it's known. But now here's the second question. So how do I find the energy of this whole system, this entire electronic system? How do I find the energy now? There are many electrons, right? How do you find the energy of the whole system? You find the energy of each electron, you just sum it all, right? And you get the total energy of the system, right? So how do I physically write it, you know? Right? So yeah.
Integrate over
Yeah.
E of k to k, integrate over that.
That's right, exactly. So I mean, from here, intuitively, it's very clear what you need to do, right? You say, well, I know the energy of E of k, right? And then either integrate or I can sum, either way, right? But typically, I want to do an integral. So I can sum from minus pi by a to plus pi by a, right? And each of them actually has 2 electrons. So that is what we are going to label always as a spin degeneracy, you know, G sub s. It is 2 here. If I have a ferromagnet and all that, it may be 1. You know, in some parts of the band structure, it can only allow 1 spin, for example. If you have a topological insulator, if you are going to the right, it has up spin. If you're going to the left, it has down spin. So it may have spin degeneracy of 1. You know? But here we have each of them is 2. It's a standard semiconductor. It's 2. So this is our spin degeneracy, right? Just from this picture. And we can pull it out, or you can keep it here. Doesn't matter. If you're somehow in some weird material, maybe you have some states, you know, that spin and momentum are locked, right? That's a topological insulator where spin and momentum get locked. Then you have to have it inside here in the sum. You can't just take it away. Here it's just 2, so I take it out. And the E total is just this sum, you know, right? Is this just sum? Not really. It also depends on what is the occupation function of that. You know, if I don't have a particle, there's nothing, you know, there's no energy there, right? Yeah.
Wouldn't all those zeros equal S below?
Yeah, I said, you know, I'm looking at a situation where only this band is occupied and this band is empty. And these are all the occupation numbers, and you know, occupation number of all the S states is 0. That's it. Okay, so that's that, and I think you can see that you know, for this particular situation, this happens to be 1, right? And clearly, that is only possible for fermions. All of them are 1, right? For bosons, you may have some, you know, other distribution. It need not be just 1. Yeah.
Are we going to include the valley degeneracy as well?
Very good point. So in this picture, in a typical semiconductor, you may have more than one valley. What does that mean? It means that in some other point in K space, so your K can be, so in K space, you may have, for example, you look at graphene. This is something we're going to do in the next assignment. In graphene, in K space, you have, you know, such a situation here, but you have another one here. It's a hexagonal honeycomb sort of structure. And in every unit cell, there are 6 edges, but this is shared between, you know, 1, 2, and 3. So effectively, you have, for every Brillouin zone, you have 2 valleys, 2 copies of this. Right? And then that's called the valley degeneracy. So you can add it here, right? So this is your spin degeneracy. That's a valley degeneracy. That once the band structure is done, you know what is your valley degeneracy. In silicon, for conduction band, it's 6. There are 6 of them. And you know, in gallium arsenide, gallium nitride, it's just 1. And graphene, it's 2, and so on. Molysulfide, it's 2. And you know, monolayer molysulfide is 2. So valley degeneracy also comes in here. Here I'm keeping it simple, saying it's 1 for this particular, just, you know, for discussion's sake. But yes, important. That's another important thing. You have to sum over all possible EKs, right? Not just one of them. If you have multiple values, you sum over that. Right? So you can see that I could also have written it as just, you know, CK dagger CK, right? But just to be more specific, C being our creation annihilation operators now, C of, you know, the p orbitals, right? P comma k and C, yeah, P comma k, right? I could have written it like that, and then said, well, here's the average, thermodynamic average. We talked about that. Remember the Fermi-Dirac distribution, the physical meaning is the occupation number operator, but the thermodynamic average of it, right? It can go between zeros and ones for whatever fluctuations and all that, but the thermodynamic average is determined by temperature. And at 0 Kelvin, it is just 1. This one is 1. If your Fermi level is somewhere here, let's say, or chemical potential is here, then that's just 1. Okay, but if it is 1, it's very simple to evaluate it, right? You can either sum it, you have the expression, right? Here's the expression. Or you integrate it. It's easier, typically, if you have a large number of sites, you integrate, and the integration is you have spin, and going from sum over k to an integration over k. The prescription is actually rather straightforward. What you are doing is, E of k, and integrating over k, but you remember you have to maintain the right dimensions. The delta k, or the separation here, is 2 pi by L, so you must divide it by 2 pi over L, and you sum over this whole thing, right? This is the same thing as the sum, really, right? And you could have summed it by writing your k as some integer times pi over a, and vary the integer from here to there, sum them all, or you integrate, either way, right? And then both of them are fine. So what are you going to get here, right? If you just integrate it all. I haven't done it, but you're integrating cosine over a period, right? That term is just going to go away, right? Cosine over a period. No, is it going to go away? Cosine over a period? Maybe I'm wrong here. A sine will go away for sure. Yeah. But an integral of a sine or a cosine over one period should go away, right? Okay. So you will just get what? 2 n EP, right? Something like that. So that's, check it. I mean, maybe that, maybe I don't know. But yeah, it's just a sum. And if you have a slightly different shape, if you have non-cosine functions, you can get some value here. But that's the total energy of the electronic band here. Okay, and this is the one way to write it. And the you could also have. Okay, I wanted to kind of switch over to give you just one direction in evaluating this whole scenario, of EK, and from this operator picture. Again, in this you can see that just to get another, if I have a photon come in, as an example, I have a photon come in, and the photon energy is exactly equal to maybe this here, or a phonon come in, or something like that, or heat body, whatever, right? A boson, which is a boson come in, and its energy is exactly equal to this, and let's say it is allowed, by symmetry laws or matrix elements, such that this electron can absorb that photon and promote itself to that energy. Right? Very much possible, right? And this is how semiconductors absorb light. Or if you heat a semiconductor, electrons can jump from here to there across the gap by absorbing phonons or thermal heat, right? It will cool, and the electron gets hot. The solid will cool. It's very much possible. And you can see that you can write now this operation, this physical process in our operator formalism, right? So you can write it, for example, this is your ground state, and how would you write this? So, yeah. Is the ground state of just the electronic system, but it's not the ground state of the entire system. So meaning the entire system includes the electronic system plus your electromagnetic spectrum. Electromagnetic spectrum has light, right? And that's a bosonic system. Photons are bosons, right? So the combined system happens to be another object which is non-electronic, but this is photon still. Or let me just talk about phonon. Why not, right? It's phonons, right? And phonons have, maybe there's large number of the phonon dispersion instead of like that. Maybe the phonon dispersion is an acoustic phonon branch, and then there's an optical phonon branch, right? These are the typically written as h bar omega versus q. Exactly the same thing, but for phonons, right? And here you can see now that the idea would be if that particular energy is here. Again, I'm just taking some guess. Maybe it's that state. This is the energy. Then and maybe there were 15 of those phonons, and and all these other states had some numbers. Phonons have no restriction on how many you have, right? And that particular state, say Q naught. So the initial state of the system is electrons are like this and phonons are like this, right? And the combination of this together is the complete system of your, the complete quantum system, right? And now this complete system transitions to a situation where you have, again, 1, 1, and all that, and then you have a 0 and 1, 1, right? And then these are all your p orbitals, and then in s orbitals you have filled one of them with this, and the others are all 0, right? Right. After this is done, you have annihilated one here, you have created one there. Right? So this electron just went there, right? But for phonons, what happened was, the same thing here, but this was 15, right? And it became 14, for example, right? So it transitioned to another state where you have this, and this was possible because of a process which involved the absorption of the phonon, which can be thought of as annihilating an electron in this k state in the p orbital, right? And then annihilating the k state and creating in the s orbital, right? The same k, or it could be different k, doesn't really matter. Maybe k plus q or k minus q, depends. And then annihilating, creating this, and then annihilating a boson in your q state.
Wait, why wouldn't the first two be B's instead of A's and the third one be a C?
Say it again? Yeah.
Why would the first two be A's and not B's? Because you're annihilating the phonon?
Oh, okay. So here's a good question. I can move this wherever I want. Okay, so you're saying that why don't we can, okay, good
Well, no,
point.
I'm saying why are the first two operators, the A dagger, A, not B's? Because are those symbolic of fermions, electrons?
Oh, I'm so sorry. This is C. Yeah, these are fermion operators. So all we're saying is we are annihilating this state, creating that state, and annihilating a boson state, a phonon state. Right? Once it absorbs it, this phonon has been annihilated. It's gone. And the way to look at it is it number went from 15 to 14 for that particular mode of phonons.
Okay.
Yeah.
How do you determine the number of bosonic states there are? So like the occupation number or
Occupation number, right. So if your system is in equilibrium with a heat bath, what does that mean? If my wafer is sitting on a chuck which is at room temperature or at 4 Kelvin, whatever, right? Then the phonon distribution in equilibrium, if it is in equilibrium, is given by, if you remember this, right, with the Bose-Einstein distribution. That's your how many phonons you have over k Boltzmann T minus 1, right? Just to get an estimate of this, if you are, let's say, this is 0. These are typical, not very high energy. Just for argument's sake, let's say you have 0.26. I think you may see why I'm doing this. 0.26 eV, let's say, right? This energy. Then at room temperature, this value will be e to the power 0.26, right? And at room temperature, kT happens to be 0.026 eV, right? And you get minus 1. And so you get 1 over e to the power 10 minus 1, right? You can do the numbers, so e cubed to the power 3. Yeah. No, what did I do here? E to the power 0.26. Did I do it right? Yeah, this number is extremely small. The occupation number of this is very small. But if I choose something very low in energy, you can calculate it. You can plot the whole thing now, right? If you're very small in energy, I should have chosen a very small energy, right? So let's say I was at 0.0026, right? Then you can see I have maybe 30 phonons or something like that, right? So this is the occupation.
And the acoustic the acoustic frequency corresponds to whatever momentum value you have, whatever k value.
Yeah. So the frequency is h bar omega, and the wave vector is q. They are completely related. For acoustic modes, I will discuss in more detail about phonons at some point later. Acoustic modes as a function of q are given by, for very low energies, it's related to the sound velocity. You know, omega is sound velocity times q. Looks like light, you know, where instead of speed of light, it's velocity of sound velocity. That's the acoustic modes. Yeah. Okay, so that's one picture. And what I want to say is, you know, if you know the band structure, even from classical, rather from single particle physics, as we wrote here, you know, from a tight binding, writing it in a in this picture of, you know, creation annihilation operators. I just wanted to outline it. I've asked you to show that you'll get the same band structure. Obviously, you get the same band structure. But in creation annihilation operator picture, you're writing the Hamiltonian as physically again as E naught, and then you create, you calculate how many, you know, how many electrons are there in site n. So you do Cn and Cn dagger, right? This is the nth site occupation number of electrons, and then you have minus T naught. Hopping, as we discussed, as I just mentioned towards the very end of last class, is you annihilate a site n and you create one in site n plus 1. That is your hopping term, right? Annihilate here and it disappears here, appears there. That's hopping. And then similarly, you can do the reverse process, go to the left perhaps, you know, and then that's your Hamiltonian for site energy for site n, but for all the sites you must sum it over all n, right? So that's your total Hamiltonian of the system. And what I wanted to say is this is exactly the same as, you know, the single particle stuff we have done before, right? In the tight binding picture, where you get this block function and all that. Here you can actually get that my energy band structure of this will be E0 minus 2 T naught cosine Ka. Almost by brute force. You don't have to go through all this analysis and block theorem and all that sort of thing. You can get it by brute force. What I mean is, you can go. What you have to do though is, I want to point this out, and when you solve it, you will hopefully make this. So these operators are creation annihilation operators are defined in what you call as the site basis. It depends on which site you are, n plus 1. So the basis of these creation annihilation operators are, you know, spatial site, you know, or xn, right? It's defined for xn. So those are the orbitals, right, physically. Now, when you go here, you see that you are looking at k's. By the way, so the total energy will be a sum over k's. Now I should write it like that. Okay, yeah. And let me write it properly. Okay, the total energy of the system will be energy of k state times whether that state is occupied or not. And now in k orbitals, we are going to switch over to k orbitals. This creation annihilation operators must be transformed from the site basis to the k basis. Right? Does that make sense? I mean, this is because when we are talking about all this business here, we are annihilating a state in Ck, creating one Ck. The orbitals are indexed not by which site they are in anymore. They are indexed by the k, or the wave vector, or the, you know, lattice, the crystal momentum, h bar k is the crystal momentum wave vector, right? So that's a new basis set, right? And so we must transform from Cn's to Ck's, right? And this transformation is actually, you know, by the way, do you see physically this is very easy to see that you can either write your total energy this way or you can write it this way, right? Because in the band structure picture, this is what makes sense to me. If I'm looking at single particle and looking at, you know, hopping of electrons picture orbitals, and maybe these are very far apart, hopping is very low. This is another way of looking at it, but they're the same thing. Right? They're giving you the same total energy in the end. Right? When we did the total energy integral, we were looking at this picture, right? To integrate this whole thing over all the k states. We were not looking at this one. Right? So this transformation, I will write down, I'll just outline it. So you have Cn and you want to go to Ck's, and I think you can see that this is a Fourier transform from real space to K space. It's a Fourier transform. And you would do, the way you would go to Ck is you can define Ck as a sum over all sites with e to the power I k xn times Cn, right? Right, and that's where your k comes in, right? The wave vector. And you may have some normalization coefficients. Typically, it's if you have n number of sites and you're going from n is equal to 1 to say big N, something like that. Right? It's a discrete Fourier transform. And similarly, Ck dagger will be the same thing, but sum again n equal to 1 to n. But this will switch sign e to minus ik and Cn dagger. Right? Remember, it doesn't matter which order you put them in because that's a number, that's an operator. You can move them back and forth. They commute. A number commutes with an operator. And from here you can show. You can also find the Ck. The commutation relations between Ck and Ck dagger, okay, or Ck prime dagger. For fermions, for Cn's and Cn primes, we know what it is. Here it will, if you choose your k's to be discrete, you will get again, k prime, same thing as it was in real space. What does it mean? It means that a state in orbital k and k prime, if they're different, the ck's you get a 0, right? And if they are the same orbital, then Pauli exclusion kicks in again, right? No matter whether you're sitting on the same site in real space or in K space, Pauli exclusion is still operational. So yeah.
Do you mind if I go back to the the electron excitation?
This one, yeah.
Yeah. So maybe it's just a stupid question, but when you say excite an electron to the conduction band, you don't just have nothing left behind. You also have a hole about the electron confusion. Can you do the operators and annihilation creation of holes?
Oh, absolutely. So, we didn't track the whole thing, the entire process through. But if I actually have this occur, if this electron is indeed excited to that state, and there is a empty state here, and the empty state is the hole, right? The name at least, right? But now the system can lower its energy, really. Physically, this is what would happen. I can take a solid, say a gallium nitride crystal, and I can shine, light on it and a photon, and it will excite. Physically, these are the processes that will happen, right? The electron will not sit here for too long. It will start emitting phonons, and it will relax to the bottom. So it will copiously, emit phonons, B dagger. It will create a lot of them, maybe 30 of them or something like that. It will create a lot of phonons. Maybe it will create them. Physically, what is going on is the electron has a very high kinetic energy. It's moving and it's colliding with the lattice, setting off all these vibrations, waves of vibrations. And this is your operator picture. It's you're creating phonons, individual modes. It is filling all these. I don't know where it is now, but it's filling a lot of these phonon states. Typically, it fills optical phonon states because they have higher energy. It fills this, maybe this. It will fill a few of these states, and you create them. And then it relaxes to the bottom. At the same time, what's going on is this hole is not sitting still either. What's going on is this electron, just like this is cascading down, that will cascade down here by emitting a phonon, and the hole moves as a result here. So you can create all these things by creation and annihilation. You can write it in that fashion. So the hole starts bubbling up, and it ends up here. And if it's a direct band gap semiconductor, then that electron will now transition and drop into that state again, and it will emit another photon out, right? And if it's a direct band gap semiconductor, and the system goes back to where it was again. Does that make sense? So this is a typical process that happens. You observe a photon, and then electrons cascade down, holes bubble up, and then it re-emits another photon. So it could have absorbed a blue photon and what may come out as a red. So this is a down conversion process. And this is obviously used heavily in many things. Especially if you are looking at TV screens, there are all these phosphors. That's what a phosphor does. It will, some of them are quantum dots and all. You will excite it with white light, but blue or red or something will come out here. Right? It may not be a crystal, but typically, I think Samsung just released this quantum dot screen, TVs. So those are really these structures. That's what's going on. And you can write all that processes using this if you want to. Okay, so I wanted to say that this is, because of, you can do this, and then because of the Fourier transform, again, you will get a e to the power minus ika and a e to the power plus ika here, and that will give you your band structure again, and you will end up with this band structure. Same thing, really. It's all, I'm saying that you can mechanistically get it by just transforming the operators from one basis to another. You get the band structure as a result. This is called the diagonal representation. We are going to the k-space here because we kind of know beforehand that this energies are diagonal in k-space. Does that make sense? I mean, that's why we're going there. So I can do this now for electrons, and I can take this and say, well, what happens if I have phonons, right? And we had started discussing this just in the last class, that if I have a chain of atoms, it could, I can close it on a ring to achieve periodicity, but I can set off lattice vibrations, right? Lattice vibrations will have energies of p n squared over twice the mass of the atom plus half mass of the atom omega square times. I had mentioned this briefly, but I wanted to kind of talk about it a little bit more today. So this is your phonon system. Total energy is, classical energy is given by this, right? We talked about, if you have a mass here, big M, which is moving with a certain velocity or momentum, its energy is, this is mass of the atom, not the electron, but the atom that's holding those electrons, right? And this is your total energy. This is the spring constant, big K, which is effectively the spring between the two atoms, right? And this is a stretching or compressing or dilating the spring, and that's your Hooke's law. Half kx squared is the potential energy. This is the kinetic energy of just vibrations, right? No electrons involved at this point, right? Okay. And so this is your phonon spectrum, and you quantize it in quantum mechanical form. This, you can see right away, it starts looking very much like a harmonic oscillator, 2 big M plus half. The only difference from a standard harmonic oscillator is you have this difference instead of a just one x, right? It's a coupled harmonic oscillator, right? It's a chain, right? And because of that, you get a dispersion relation again. If it was just one mass and one spring, right? If it was just one mass and one spring, you will get one harmonic. It's one harmonic oscillator, right? Here it's a displaced. It's a chain, but again with analogies to classical physics or by complete brute force, you can actually write down, fully quantize it, and write it in operator formalism again, right? So the way this will end up is this maps exactly to the phonon Hamiltonian maps exactly to a nice harmonic oscillator picture where you have h bar omega q, where your dispersion. You may have solved this in other courses where here's acoustic phonon dispersion, right? Typically it goes as sine. So at high Qs, it also has its same sort of Brillouin zone from minus pi by a to plus pi by a, and it has its own orbitals too, right? They are also separated by 2 pi over L, just like electrons. Right? Just like electrons, they're all separated by 2 pi by L, and I think maybe you have done this in because you see half m x dot square plus you can just substitute x is some constant e to the power ikx, and you get this whole solution ikx minus omega t. If you do that, you substitute into this equation, you can solve the whole energy differential equation, and you get this dispersion that the omega for acoustic modes is given by square root of k by m times 1 minus cosine qa, or sine qa by 2 and all that. Right? So this is what you get. You can plot this absolute value of that actually. Yeah. So if you look at any introduction to phonons, you will see this picture, right? So, yeah. So what I'm trying to get to though is the quantum version of it is that each mode of these phonons, each of these modes, is a harmonic oscillator, independent harmonic oscillator, and what you get is the total energy of that is again you can write it as BQ dagger BQ, right, plus half. This is any single harmonic oscillator, but you have you can think of it as 2n. You can consider 2n. If it was light, I would say 2n because it has polarization. It has left-handed or right-handed. This is effectively the spin of light, if you might. But again, regardless, there is some sort of if there's a phonon degeneracy, I don't want to get into that. Essentially, what you're getting is the sum over q's here, okay? And this is your analog of the electron picture. The electron Hamiltonian had. You can see that very interestingly, your electron Hamiltonian is also written in terms of number operator. Right? It's a fermion number operator with the eigenvalues in its diagonal space. The diagonal space of electrons is the crystal momentum or K space. Right? The electron is not diagonal in real space, but it's diagonal in momentum space. It's kind of natural because waves are, defined by their modes, which is related to k, not the x. Similarly, the phonons are diagonal in their k vector space, or we are calling it as q, which is a 2 pi by the wavelength of the phonons, and this is the diagonal. Right? Remember, they are okay. So this is the diagonal version of it, and this is the number of phonons in any mode now. Right? Physically, that's. And I'm trying to emphasize it. Maybe some of it is repeated from last time, some aspects of it. But this is kind of I would say today, the best known theme of electron-phonon interactions on many particle system. So you have electrons in a solid that are whizzing around. Maybe they collide with this, they excite phonons, and energy is going back and forth between the Ek and the omega k here. Right? So it's going back and forth. Momentum is going back and forth between the two. So the total energy of the system is written as the electron plus the phonon or photon, if you might. I mean, whatever I said about, maybe you can tell me what is the dispersion of photons or light. Energy of photons is related to 2 pi by wavelength as what? Right? So energy of a photon is actually momentum times speed of light, right? P times c, and momentum is always h bar times q or h bar times k, right? So energy of a photon is linear, and whenever you have linear, you have no curvature. That's why you call it massless. It has no mass. Curvature is mass. If you have no curvature, there's no mass, right? Acoustic phonons at very small energies are massless. They're like, and the speed is sound velocity instead of light velocity, right? So, yeah. So either photons or phonons, I'm just writing it like that here, plus any exchange between the two. Any exchange between the two, electrons and photons or electrons and phonons, right? This is the total Hamiltonian. You can write it now as we wrote earlier. Conceptually, it is very easy to write. You say, well, I'm just going to go to the basis in which is diagonal. Okay? And let's say I have already found all the energies in that basis, and those are EKs. That's the band structure of a solid, right? And then I write it as, right? So that's your any solid you think about, metals, semiconductors, insulator, whatever, you can always write it like this, right? And obviously there's a lot of work that goes into calculating this EK, but physically it's very clear what you're doing now, right? Similarly, you write it as phonons, and you write it as sum over q's of h bar omega times bq's and bq dagger plus half, because it's a bosonic system. It looks like this. It's a fermionic system, a boson system, plus so I can write it as q and k, and I will write just as a coupling coefficient, the strength of electron-phonon interaction or strength of electron-photon interaction. I'm just going to write it as v k sub q, something like that, right? And this here in this term, you have to write down exactly how is this interaction happening. Are there two photons being absorbed? But it is a function of CKs, CK daggers, right, and BQs and BQ daggers, right? Does that make sense? That will take care of all that stuff, right? And that is the total energy of the system, and that this is acting on your state of the system, which is composed of maybe all filled and maybe 20 here, and it acts on this state, this entire state, and it converts into another state or another state. So this is the whole transitions which cause transport of electrons, maybe in the band or interband or something like that. So this is the picture. Yeah.
Does that account for correlation as well?
Yeah. So good question, right? So I'm getting there now, right? So I wanted to kind of finish. So correlations. So for example, electrons can. Let me just say one more thing before we go to the correlations right now. Yeah? So now this is your whole Hamiltonian, and you can see it's in some sort of a mixed K space and Q space, of electrons and bosons, mixed space, and you can think of this as a completely new state of the system. And a very interesting question to ask sometimes is, can this composite system that is composed of electrons and say phonons or electrons and photons, can I diagonalize this whole thing again? Right? And that's a very interesting question, because if you can diagonalize this whole thing all over again and find another situation, if you can write this whole quantity as a sum over some other kind of, maybe creation operators with k's. I don't want to maybe lambdas, and annihilation operators of lambda, and then you find some e lambdas. Do you know what I mean here? I'm saying, if you can diagonalize this whole thing here in this way, right, then first thing is you have become very famous now because you have discovered a new particle or a new quasi-particle. This is the meaning of, basically this whole system has excitations now which are composite, combined of maybe two electrons and one phonon, for example. That's a superconductor. Superconductor is at least one kind of, the BCS type of superconductor, where you have two electrons and one phonon, which interact in a way that they form a composite object now. It's a correlated object. I think it's kind of getting there, right? So two electrons get so strongly correlated by exchanging phonons that this composite object of one, two electrons of and a phonon that goes back and forth, bounces back and forth if you might between them. That's a new object, and the system is allowing ground states in that with that as your new particle. It's a new particle that, or quasi-particle. It's a combination of things. You can have an electron and a hole and a photon combined together, or electron hole combination that traps light, and that would be typically excitons and polaritons, and all these are excitations which are composite objects. Polarons, all these are collective excitations, correlated objects typically, and generally right. So, and later on we will encounter this. For example, in the superconductivity, you will see that it can be done. It can be diagonalized, and and you will end up with new composite objects that are, essentially composed of 2 electrons and some other things, for example. Right? So you start with some elementary particles and you end up with something else which is composite, but if your energy is diagonal, that means you will, when you experimentally measure it, you will find that particle. And this has led to, I think one of the big examples is the Higgs boson. I mean, that's clearly was predicted from this sort of diagonalization, and it took many years, but it was found, right? And quite a few others. So, okay, so I have asked you something about it, but just to in semiconductors, you can also have objects which are so correlations will actually correlated transport properties are very interesting, but way we will encounter it is, for example, if I have sites here where there are electrons that are already occupied, okay, and clearly that if I want to put 2 electrons at the same site, I'm going to have to pay the Coulomb energy cost. They're both the same charge, right? So I have this minus E squared by 4 pi epsilon r energy. This is a repulsion potential. This is the energy price I have to pay to put, and r is very, very small, so it blows up. It's a large number, right? So putting 2 particles in the same site does cost energy, right? And if I have what you can see is if I have one particle missing here and another particle missing here, and if there is a very high cost of putting 2 particles at one site, you'll see that if I move this particle from here to here, it becomes easier, for example, for this to move from here to here. So they become like a rigidly connected object now. It's somewhat like a correlator. We'll see that sometime later. So something here influences, and so the system starts behaving as bigger than just point particles. And the biggest, or rather the most drastic realization of this is a superconductor, where every one of the Cooper pairs in the superconductor acts as one object. The whole thing is one quantum object. All Cooper pairs together, you have just one wave function for all of them, and they move rigidly. So that's why there's dissipation less. There's no dissipation there. We will look into that. Okay. Yeah. Okay. So I wanted to do maybe in the last 5 minutes just tell you a little bit about the next couple of things here. So I've given you 2 handouts, and I've given you 2 problems from these 2 handouts, and I wanted to just ask. So this is a chapter from Herb Kromer's book on quantum mechanics, and the first part of this chapter, please read it. There's a reason I asked you to look into this. In the first part of it, we have really covered and I have discussed some aspects of it. The expression for the current and probability interpretation with the wave function, and then he's talking about what sort of transmission. Okay, so just wanted to switch. So I'm going to not talk about the many particle aspect of it for perhaps about 2 or 3 weeks now. I'm going to go back to single particle all over, but I wanted to get it done because if some of it excites you, some of you think, oh, this is intriguing, I want to learn more, you can choose as a project. There's a very good way to learn more. So I'm going back to single particle, and I'll come back to once I'm done with single particle, we'll come back. Single particle transfer will come back to many particle, and then we'll use this. Whenever in single particle picture we encounter a situation where we might use this formalism, we will use it too. So yeah. Okay, so the chapter essentially is related to telling you how, if you have arbitrary potentials in the path of electrons, how do you calculate currents? Right? So that's any arbitrary potential. And as you can imagine, it's extremely powerful way to. So essentially, you are solving the quantum transport problem of single particles once and for all. This is any arbitrary potential. you solve it. And you can find out if I have electrons incident at that energy or that energy or that energy, what is my net current flowing on this side? Completely quantum mechanical picture. And one of the problems here is it asks you to set up your own little code. By the way, this is let me tell you, this is actually relatively straightforward to solve. And if you can set up this code, you have already solved one of these earlier. I've asked you, but okay. It goes through quite a bit of details and examples of various kinds, periodic crystal, this, that. But here's the problem I asked you to solve, to do. And you can set up a little code which will calculate this property and as arbitrary number of discontinuities of arbitrary lengths and all that. And then he asks you to solve it for a particular case, and you'll see what is the current that will flow in that. And the whole method is you have solved it earlier by looking at reflection coefficients, transmission coefficients, right? The basic idea of this transport picture was if I have a barrier or a well or whatever, right? I will have, and I have incident electrons here. I'll have some reflection coefficients, some transmission coefficients, right? And using my quantum mechanical description of, J, or the quantum current, the expression that we derived, you can write that, on the right side, for example, you have h bar k2 over mass is the effective velocity times mod t squared is your probability, number of particles, or density of particles, if you might. And similarly, you have on the left side, you have 1 minus mod r squared. This is something we had talked about, if you remember, h bar k1 over m, right? That's current flowing here, current flowing there, current flowing here, all of them you can find it now, right? Now, if your energy is lower than the barrier height, you will have tunneling, you'll have transmission of evanescent states. But if you set up this matrix, all of that is taken into account. Essentially, it'll, if you set up this sort of a, as you can imagine, if you have an arbitrary potential, you cannot write down an analytical expression for the, because it's an arbitrary potential, right? You can write it formally, but you cannot solve it completely. But what is writing here is you have a matrix. You set up this matrix with cascades. If you can find regions of uniform potential in a multi-structure. Oh, easy here. We can. Thank you for bringing it in here. We can keep it on that side. Yeah. Oops. Sorry. Right. There's just one limitation here is that is asking you to look at it as flat regions and not curved regions. But you can imagine if you have a curved region, you can break it into many small flat regions, right? And so it's set up really for all cases. And then when you write it, I think you can see how these wave functions look. It should make intuitive sense that you have a certain amplitude, a certain wave vector k here, which is different from maybe the wave vector there because its potential energy is different and all that, right? The wavelength here is larger, wavelength here is smaller because the kinetic energy is smaller and all that, right? So you just set it up, and what you're solving for in the end is every interface like this is connected to the next. Your amplitude's wave function is continuous, derivatives are continuous, and you get this what's called the transmission matrix, which is a cascade of all these things. And then from here you can calculate your total currents. If you know your amplitudes and all that, you can get the currents. So I'll suggest you read it. I'm not trying to kind of say that I'm discussing this at this point, but single particle transport is essentially completely solved. Here's a transmission probability. If you find this cascaded matrix that he describes, you take 1 over that mod square, you get your total transmission, and you get it as a function of all energies that of incident electrons. And in a realistic situation, when you calculate the total current in a semiconductor metal, say Schottky diode or something like that, or a MOSFET or heterojunction, you calculate this transmission probability for each energy. But the question you must also answer if you want to find the total current is, how many particles are there at that energy, right? Typically, if this is a metal, you will have a Fermi-Dirac distribution, and the number of particles at any energy will follow 1 over your Fermi-Dirac distribution, E minus Fermi energy over kT plus 1. So you then just weight the transmission. So the way you will find it is, if you find your transmission probability, then you must weight it with the occupation number of the source electrons here, and then you sum it over all energies, and you get the total current. Does that make sense? What I'm trying to say? So Fermi-Dirac distribution will play a big role, and that's what is going to lead to every exponential relation you see in a diode or a Schottky diode. This e to the power qv by kt comes from this Fermi tail. In the tail of electrons, they'll go over. So this you will see in the assignment problem in the other handout. This is also a very nicely written chapter. This is from Mark Lundstrom's book on transport, first chapter. He also gives a good summary of the entire subject. And I've asked you to, he talks about band structure, you can kind of read through it, but I've asked you to solve just one problem from here, which is related to the Schottky diode, where you have a metal and a semiconductor, and you want to show that the current that flows across it is given by some constant e to the power qv over kt minus 1, where v is the voltage. So I will start outlining a few things that will help you along this direction too in the next class, but I suggest you start reading these two, because I want to, in this course, also make sure that you understand that I wanted to cover some of the more researchy topics. This is kind of the basis, and you have to have the basis here. I'm very happy to spend a lot of time going through the more basic parts, which are typically covered in a solid state physics or other quantum course. But if you feel that the matter here, if you start solving the problem and say, well, I'm not completely comfortable, please come to me and we will discuss it. I will, based on how many times I hear that, I will spend some time in the class too to discuss it. But I would suggest you also do some reading of your own, and especially the handouts here, and pick this part up. And I wanted to emphasize more. I will solve some examples. Let me just put it this way before I move on to the next topic. I wanted to get to the transistor, the ballistic transistor, and quantized conductance as the next topic. But before that, I just will perhaps in Tuesday's class, I'll talk a little bit about both this and the 1D transport problem, the general potential. So I'll just briefly talk about that. Okay, good. So I think I'm done for today, and we can meet next week then.